Okay. Hello, everyone. My name is Emmy Hughes. I'm a first-year PhD student here at Georgia Tech, working with Dr. James Ray. And today I'll be talking about geochemical and mineralogical evidence against hydrothermal conditions in Eridania Basin on Mars. So I'll take you through the title a little bit. I'm using geochemistry and mineralogy on sort of regional scales, so sort of coarse resolution but broad coverage to sort of investigate the extent of hydrothermal conditions in Eridania Basin. It's a sort of ancient basin system on Mars, dated to sort of early Martian, potentially habitable time periods that may have had and hosted a hydrothermal system. And so I'm investigating whether the regional geochemistry and the mineralogy sort of corroborate the existence of that system. And as you can see by the word against here, maybe we're seeing that it might not. So just to sort of back up a little bit and think about the Martian regolith on broad scales, we know that Mars is mostly basaltic, so sort of relatively primitive igneous rocks. And we know that the regolith is composed of that primary basaltic material, so you have mostly pyroxenes, plagioclases, and olivine minerals. But we also know that, there's been some water alteration processes that have happened on Mars, and the production of secondary minerals from the sort of alteration of that primary basaltic mineralogy. So you get things like sulfates, chlorides, carbonates, clays, and hematite. Here are some lovely hematite sort of nodules that are called blueberries that were identified and are really nice evidence of secondary alteration processes. We also have some iron sulfates up here that you can see from the rover tracks from the Spirit rover. So when that rover was sort of doing its daily business, it unearthed some interesting geology that there's this sort of layer of iron sulfate in the Martian regolith. So as you can see, we have a few different ways of constraining that mineralogy. We have in situ data from Ridiani, Gusev, and Gale, and now, of course, Jezero with our Perseverance rover. We also have these iron sulfates, and then we also know that there's some soil variation potentially across the Martian topographic dichotomy. But there are also some unknowns, and some of these unknowns include whether or not the soil is relatively homogeneic or sort of the same as a global unit across Mars, or whether it's more locally derived, whether you have sort of erosion of local bedrock and it might be more heterogeneic across Mars. We also don't necessarily know the mechanical and the chemical pathways of alteration and whether we're getting sort of in situ alteration ongoing now, if maybe we're even forming low pH brines on Mars on the modern surface. And finally, we don't really know if there's sort of soil horizons or stratification or if it's relatively homogeneic on a sort of lateral dimension or looking up and down. So we have some data sets that we can use to investigate these kinds of questions. One of the main ones I'm working with is gamma ray spectroscopy data. So this is sort of gamma data. It gives you elemental abundances for Mars, and you can see that it's about 5 degrees by 5 degree pixel scale, so relatively coarse-grained. You can use this to reconstruct the sort of regional differences in geology and sort of understand the kind of large-scale geologic history of Mars. So we have a variety of mineral-forming elements that we can constrain with gamma-ray spectroscopy data, but there are some that we don't have, and this includes magnesium, phosphorus, sodium, and manganese, all of which are important mineral-forming elements. So it's important to figure out a way to constrain these abundances if we want to get at the total mineralogy of Mars. We also have thermal emission spectroscopy data, so this is relying on the emissivity of the surface minerals. Because of that, we can't get coverage for all of Mars, so there's relatively dusty areas for which we don't have sort of surface mineralogical data. But we can use it to derive a series of sort of classes that can tell you about sort of global variations in mineralogy, and so that's the map that you're seeing here. So these two data sets combined, we can sort of integrate them to understand the overall mineralogy of the Martian surface. I'll just take a pause and catch my breath a little bit. My mask is making it troublesome to breathe. Give me a second. Okay, so our overall process is integrating these two data sets. And so there's been some previous work that's done this. This is using in situ data for Mars for Spirit and Opportunity rovers. So for these data sets, we have rover capabilities to do geochemical data using APXS data. We also have what's called mini-tests, so that's sort of a small thermal emission spectrometer, and we can use those data sets to integrate them to get at the total mineralogy of both primary and secondary minerals. So for our work, we're substituting gamma ray spectroscopy data for APXS data, test data for mini-tests, and then we don't have Mossbauer data, so that's that's iron minerals, so we use test data. And sorry, I actually might take my mask off. I'm having a little trouble breathing. Thank you. Okay, so I'm going to pop through this quickly because I've already talked about that. Okay, yeah, so we need to derive additional elements that we don't have constrained via gamma ray spectroscopy data. So a lot of my work was doing that. So I developed a variety of methods, including ratio methods, regression, and mass balance approaches to get at some secondary, or to get at some additional elemental concentrations and abundances. And I can talk about that in detail if people want to hear about it. But generally speaking, I've derived a sort of robust way of getting at additional oxide abundances that aren't constrained with GRS data. And here are some of these sort of ratios that are at play here, using both sort of meteoritic data, in situ data, so on and so forth. And then I've reconstructed some maps of what magnesium might look like across Mars, and also the other oxide abundances. So this was successful. And so now that you have a sense of the methods that we're using and why we're using them, we can talk about Eridian Basin in more detail. So this is Eridian Basin here. You can see that there's this sort of, maybe you can see it, this sort of channel system that's kind of up in the north. So this is what's called Madam Vallis, and up here is Gusev Crater, the landing site of the Spirit rover. An Eridian Basin may have been sort of a large system for, through which this channel was connected to Gusev Crater that in the Noachian era may have been, for a sort of a long time, hundreds of millions of years of scale, had a Paleolake Basin. And this Paleolake Basin may have also hosted a hydrothermal system. So in 2017, Joel Michalski published a paper about the possibility of an ancient hydrothermal seafloor deposit system here. So there's a lot of secondary minerals that are indicative of this potential system. And then in 2021, Luju Oja, who is a graduate of Georgia Tech's PhD program, published a paper that maybe the system was heated amagmatically by the decay of radiogenic heat-producing elements, including thorium and potassium, which are both enriched in this region. So there's some evidence and some recent sort of push towards an ancient hydrothermal system in this area. And some of the evidence for this comes from the mineralogy. It also comes from magnetic anomalies that we see that may be due to the presence of magnetite induced by serpentinization of the olivine-rich crust. We also see these radioactive element enrichment, which may be decaying and leading to that thermal gradient. And here is the sort of overall scope for what Eridania may have looked like. Here are some deep basin deposits. And then here's how the system may have worked according to the Michalski paper. And so the more recent paper suggests, here's our sort of region of thorium and potassium enrichment. Here are our magnetic anomalies. So overall, it seems like there's some sort of global data sets indicating the presence of this system. But there's also been pushback against that idea. So in 2020, Dr. David Leverington posted a paper that sort of interpreted the signatures that were previously interpreted as fluvial or lacustrine as potentially low viscosity lava flows. So reinterpreting these kind of geomorphic features, and also suggested that the abundance of secondary minerals that we're finding in the Eridania region are not significantly more enriched within the topographic confines of Eridania than they are outside of it. So maybe this, wasn't necessarily a putative Paleolake after all. So that's sort of the impetus for our work here. So we derived the mineralogy for the region using a couple of different geographic constraints based on t-tests of the abundance of both thorium and potassium, and we got at the sort of bulk average mineralogy for the region. And as you can see, we see mostly sort of relatively unaltered mafic mineralogy. So we've got very high olivine abundance, and if you know anything about olivine, it weathers very quickly with just a little bit of water. So if this lake existed for hundreds of millions of years, we shouldn't see such high olivine abundances. We're at about 28%. We use two different methods of deriving the magnesium. You can see that they're corroborating each other quite well. So that's a pretty good sort of indication that we've got high olivine here. We've also got about 10% of secondary minerals in total. So that is, that's a lot, but it's not necessarily more than the Martian crustal averages for those. So what we're seeing here is relatively unaltered mafic mineralogy, which is not consistent with what you would expect for a long-lived hydrothermal system. So in order to look at a different data set and maybe sort of investigate, if there are other ways to corroborate that, we were looking at CRISM data, which is visible to near-infrared spectral data of the region. So these are lots of the sort of CRISM stamps that I investigated, and we were looking specifically for amorphous silica, which is a very useful mineraloid for reconstructing a paleo environment because the sort of shape and the depth of the absorptions can kind of tell you the extent of interaction with water. So it can be a proxy for hydrothermal versus epithermal conditions, and so on and so forth. So we were looking for this mineraloid in order to do that kind of reconstruction. We found 2 CRISM stamps that had amorphous silica. They are up here and over here. So these were our 2 kind of main ways of being able to derive insight into that question. And both of them seem to be in sort of paraglacial or aeolian settings. So in this CRISM stamp, we see mostly what looks like redistributed aeolian amorphous silica. And then in this CRISM stamp over here, which I'm showing just here, shows this sort of sawtooth pattern, which I'm not sure how well you can see on this structure. And that's more indicative of relatively recent paraglacial processes. So neither of these seem to be sort of bedrock settings or consistent with sort of kind of a hydrothermal system, but maybe more something like redistribution or paraglacial processes. And this was corroborated by our spectral analysis. You can see some of our data plots in the area of aeolian and paraglacial or in the sort of overlapped region, but nothing very clearly indicating bedrock. And we do that by looking at the sort of position and the depth of the absorptions that you can see here in this VNIR spectral plot. So we've come up with 2 different models that we're sort of offering for the overall region. One of them is a mafic volcanism model, which does not necessitate any hydrothermalism at all. And so we suggest that the secondary minerals may have been formed by incipient alteration of the basaltic material or sort of fumarolic action. So if you have sort of explosive lava flows where you get, or explosive volcanism where you get a lot of volatilization, these can sort of quickly alter your ash and potentially lead to the formation of those secondary minerals that we're seeing. We also offer a hydrothermal and mafic model where you have some hydrothermalism, but you also have some effusive low viscosity volcanic flows that then sort of create a mafic cap essentially over the evidence for hydrothermal minerals. So these are our sort of 2 ways of potentially tying everything that we're seeing together, the secondary minerals as well as the evidence for sort of a mafic mineralogy overall. So our conclusions are that the magnesium in the Eridania region is on par with global crustal averages, which is not something I went into, but is about true. The regional mineralogy is consistent with unaltered basaltic material. And finally, that spectral analysis seems to indicate that the amorphous silica is more consistent with aeolian and glacial activity than it is with hydrothermal activity. So thank you. Oh, I'll also thank James Ray, Dr. Suniti Karuna-Tilake, Don Hood, Gus Bates, and Alka for their help with this. But thanks very much.
All right. Does anybody have questions? I think we have time for about 1 question. Anybody online either? Is there any questions? No? Okay. We have a question? All right, sweet.
When you talk about these hydrothermal systems, are these proposed to be low temperature or high temperature?
I think this would be relatively high temperature. I guess depending on, the concentration of these radiogenic heat-producing elements, sort of in the upper crust, I guess. But yeah, I think it'd be relatively high temperature. If you wanted to look into it in more detail, the OSHA 2021 paper provides the thermal gradients that you'd expect. So yeah. But sort of centrally, there is sufficient sort of energy gaps or gradients in this kind of in this expected hydrothermal system for exploitability by life.
Cool. Thank you. All right, sweet. Thank you so much, Emmy. That was awesome. Our next speaker will be Abigail Russ, I believe on mud volcanoes.